Okay, so this is a discussion on the material in section 4.2, Rolle's theorem and the mean value theorem. So this is another one of those topics that I think if you're an engineering student, you may never see it again outside of this course. I'm not sure if I don't remember if you see it in Calc 2 or not. It's very standard to see this in the Calculus 1 course. If you're a mathematician, let's say you love math, you like proving theorems, and you like really, know the proofs. The mean value theorem is probably one of the more important theorems in mathematics because it's used to actually prove other theorems. But let's just talk a little bit about what it is. Okay, and I think that this picture, yeah, a picture is worth 1,000 words. Okay, so let's see here. So I'm going to see if I can draw a straight line towards this. Okay, so right here, this graph right here. And what it's saying is, so we have this picture, it's kind of this kind of segment of a function. And so it's concave down. And so if you look at there's this line, the secant line connecting the endpoints. And what it's saying is that there's a tangent line somewhere. So there's this point C. So let me just start again. You have this secant line connecting the endpoints A and B. Okay, and what the mean value theorem says is there's some point in between A and B that the tangent line at C is parallel to the secant line connecting A and B. Okay, so basically that, so f of B minus f of A divided by B minus A is the average rate of change. And at some point in between A and B, the instantaneous rate of change is equal to the average rate of change from A to B. Okay, so this is the famous mean value theorem right here. Okay, and students, I don't expect you to, you might see problems with it. So you want to be familiar, when you see it, oh, I know what to do, how to solve this problem. It's not necessarily something you need to kind of say off the top of your head. Okay, so if f is continuous on the closed interval AB and differentiable on the open interval AB, then there's some number C in between A and B, or in this open interval AB, such that f prime of C, the instantaneous rate of change at C, is equal to the average rate of change from A to B, or f prime of C is equal to f of B minus f of A divided by the quantity B minus A. Okay, so now Rolle's theorem, typically, if this is a course where we did proofs, we would prove Rolle's theorem first. And then Rolle's theorem would then be used to prove the mean value theorem. But Rolle's theorem is really, the mean value theorem is a generalization of Rolle's theorem. So Rolle's theorem says, let's say f of A is equal to f of B, right? So that means that this numerator would be 0. And all it's saying is that there's some point C in between A and B such that f prime of C is 0. Or there's a horizontal tangent line somewhere between A and B. And so that's what we see right here. Okay, so in this drawing right here, f of A equals f of B. Yeah, so we see that the secant line connecting A and B is just a horizontal line. And that there's some point, the mean value theorem would tell you that there's some point C in between A and B such that the tangent line is just a horizontal line. Okay, so let's just look at, so students, a lot of these problems, we're actually asked to find the point C in between, we're given endpoints. We have to calculate the slope from A to B, and then we have to find the point C such that f prime of C is equal to the slope of the tangent line. But the whole idea behind the mean value theorem is that we just know that this point exists. We don't necessarily know what the point is. So actually, I did a problem from the homework too. So a lot of this is just applications now, simple applications of the mean value theorem and Rolle's theorem. Okay, so let's just look at this problem right here. So you have this polynomial x squared minus f of x plus 4 on the closed interval -1, 6. So polynomials are continuous everywhere. They're actually differentiable everywhere. And again, for our course, the only time it wouldn't be differentiable is if you had the denominator of the derivative, it was 0 somewhere, or you had the absolute value, some kind of absolute value function. Okay, so it shows that Rolle's theorem can be applied to f on this interval. So in other words, we have to show that there's some point C in between -1 and 6 such that f prime of C is 0. So first of all, we have to, before we can say, first let's just verify that the conditions of Rolle's theorem exist. This is actually probably one of the more interesting parts of the problem. Can we actually, before we just start applying the theorem, let's make sure that the theorem actually applies. Well, I already said two parts of it. It's continuous and it's differentiable. So Students, you can just, again, if there's no absolute value involved, if there's nothing in the denominator that makes the derivative 0, then you can assume that it's differentiable. Okay, so so to prove that, to verify Rolle's theorem can be applied, we have to show that f of -1, right? So here's our f, x squared minus 5x plus 4. We have to show that f of -1 is equal to f of positive 6. And you just plug in the numbers and you see f of -1 is 10 and f of 6 is 10. Okay, so the Rolle theorem says that there's some point C, -1 is, does that look like a C? -1 is less than, I'm not really sure, let me try it again. -1, that there's some C in between -1 and 6, such that f prime of C is 0. So in our case, we can, because this problem is simple enough, we can actually solve for C, right? We know that the derivative of x squared minus 5x plus 4, we know that it's 2x minus 5. And so you just solve that for 0 and you get x, turns out it's 0 at 5 halves. And you can verify that 5 halves is in between -1 and 6. But I think the interesting thing, like in a more advanced math course, the interesting thing about Rolle's theorem and the mean value theorem is that we just know that that this point exists. We may not be able to find, maybe the equation isn't that easy for us to solve. In this case, you kind of don't need Rolle's theorem because it's so easy to find the C. Okay, so, and here's another one now with the mean value theorem. And I think, let's see, should we do this one here? Yeah, so let's just do this one and then I will, and I'm not going to do anything hard. There aren't going to be any word problems with the mean value theorem on the quiz. Okay, so find the values of C guaranteed by the mean value theorem. So now we have this function the square root of the expression or of the quantity 2 minus x on the interval -7, 2. So okay, so the domain is all numbers 2 minus x greater than or equal to 0 or x less than or equal to 2. So f of s, the function square root of 2 minus x is well defined if x is less than or equal to 2. Like if x is 3, now you're taking the square of a negative number, right? But if x is less than or equal to x is less than or equal to 2, this function, the square root of 2 minus x, is well defined. And you actually have this graph here. I think it's that blue font right there. Okay, so now what the mean, and it's also continuous, right? So we can actually draw the function from -7 to 2 without lifting our pencil. Okay, and so there's nowhere where the derivative is, the denominator is 0, where the derivative has a 0 in the denominator. Okay, so now what the mean value theorem says is that there's some point C that, so we see in this dashed line there, that's the secant line connecting -7 and 2. And so the mean value theorem says that there's some point C in the open interval -7 to 2, such that f prime of C is equal to the average of f of b minus f of a over b minus a. Okay, so that the instantaneous rate of change is equal to the average rate of change. And that's all. That's all really the mean value theorem tells us. It doesn't say it's easy to find the C. Now these problems are set up in such a way we can find the C, but typically, like if you were, in a more advanced math course, look, such a C exists, and that's all you'd care about. Okay, so but let's see if we can actually find the C. So just to also reinforce our equation solving skills. Okay, so the derivative of the square root of 2 minus x. Okay, so we're gonna have to use the chain rule. So we drop down to 1/2, subtract 1 from the exponent. So the exponent is -1/2. And see, there's a minus x in there. So we actually have to, so the derivative of 2 minus x is -1. So we make sure and use the chain rule. So the derivative of the square root of 2 minus x is -1/2 times, it's negative, it's right here. I'm having a hard time saying that. It's -1/2 times 1 over the square root of 2 minus x. Okay, and that is differentiable in the open interval from -7 to 2. See, the denominator is 0 at x equal to 2, but we are, so it's not differentiable at the endpoint, but we only care about the open interval. And so now we just have to solve. Okay, so let's find some point C. So here's the derivative, just plug in C. So let's find some c such that the derivative, so this f prime of c is equal to the average rate of change. So we calculate f of 2 minus f of negative 7 over 2 minus negative 7. And it turns out f of 2, yeah, you plug in 2, you get, square root of 2 minus 2 is 0. You plug in negative 7, you get the square root of 3. So it's 0 minus 3, and 2 minus negative 7 is 9. So the average rate of change is negative 1/3. And you want to find some point c such that f prime of c is negative 1/3. Yeah, so now you just solve this equation right here. Negative 1/2 over the square root of 2 minus c is negative 1/3. And I think you can follow the logic here. You get that c is equal to negative 1/4. Here, let me just do one more here. This is out of, is out of the homework. Doesn't like me. Okay, here we go. Okay, so this is problem number 11 out of the homework, similar to the one we just did. And you'll see these are the kind of problems you'll see on the quiz. So now we have a similar function, 3 times 1 over the cube, 3 times x to the negative 1/3. And we want to see if the mean value theorem applies from 1/8 to, on the closed interval 1/8, comma 8. Okay, so first we want to, determine whether the mean value theorem applies to the given function on this interval, a comma b. So, well, the only place where that, if you actually look at the function's continuous, the only place where that function is not continuous is at x equals 0, right? Because you have 3 over the cube root of 3. Okay, so the only place where that's 0 is at x equal to 0. Well, 0 is not in that closed interval 1/8 to 8. And also, then if you take the derivative, once again, you're going to have 1 over x to the 4/3. And again, the only place where it wouldn't be differentiable is x equal to 0. So it's continuous on the open interval, 1/8 to 8, and it's continuous on the closed interval, 1/8 to 8, and differentiable on the open interval. So the answer is D. Yeah, we got all these choices. I didn't even read A, B, and C because I knew the answer was yes. There's only one yes. Okay, I know the mean value theorem applies because it's continuous on the closed interval and differentiable on the open interval. Okay, so now B. Select the choice below, and if necessary, fill in the answer to complete your choice. Well, we know it's not B. We know the mean value theorem applies. So now what they're saying is find C such that f prime of C is equal to the average rate of change from 1/8 to 8. Okay, so the first thing we have to do is, okay, so now we have to take the derivative of, they kind of set it up nice with it. They put the 3 in front, so we multiply it by negative 1/3, that goes away. Okay, so we're going to take the derivative of this function right here, 3 times x to the negative 1/3. So we just drop down the negative 1/3. So it's negative 1/3 times 3, and subtract 1 from the exponent. We get negative 4/3. And yeah, so the derivative turns out to be negative x to the negative 4/3. Make sure you don't, it's easy just to kind of forget about that negative sign. And if you do, then we guarantee to get the problem wrong. Okay, so even if most of our work is correct. Okay, so that's the derivative. Okay, so now we want to find, the average rate of change. Okay, so we find the slope so we find this quotient right here. F of 8 minus f of 1 over 8 divided by 8 minus 1/8. Okay, so remember f is equal to, is 3 times, remember it's 3 times x to the negative 1/3. That's our function. Okay, and so we just plug those numbers in. So it's 3 times 8 to the negative 1/3 minus 3 times 1 over 8 to the negative 1/3 divided by 8 minus 1 over 8. Okay, so the denominator turns out to be 63 over 8. And 8 to the negative 1/3 here that's just 1 over 8 to the 1/3 or 1/2. And 1 over 8 to the negative 1/3 is the same as 8 to the 1/3 or 2. Okay, so we end up with this quotient right here. So 3 times 8 to the negative 1/3 minus 3 times 1 over 8 to the negative 1/3 over 63/8. Okay, so 1 over 63/8 is that's just 8 over 63. That looks, no, that's 36. 8 over 63. Okay, so this quotient right here, okay, so the denominator is 63 over 8, that's 8 over 63, and then the numerator is 3 times 1/2 minus 3 times 2. We just do all this arithmetic. Let's try not to make a mistake, which is easy to do. Just factor out the 3. So it's 8 times 3 divided by 63, 1/2 minus 2, or 8 over 21 times negative 3/2, or negative 4/7. Okay, so the quotient f of 8 minus f of 1 over 8 divided by 8 minus 1/8 is negative 4/7. And we know that the derivative, do we calculate the derivative somewhere? Yeah, it's negative, the derivative function is negative x to the negative 4/3. Okay, so now what we do is we want to finish the problem, we want to find the c in 1/8 to, in the closed interval, no, in the open interval 1/8 to 8, such that f prime of c is equal to negative 4/7. Okay, so the derivative function was minus x to the negative 4/3. So we just solved minus c raised to the negative 4/3 is equal to minus 4/7. Okay, just multiply sides by -1. So you get c to the negative 4/3 is equal to 4/7. Now just, get rid of that negative exponent. So just take the reciprocal of the right side, or take the reciprocal of each side. So c to the 4/3 is equal to 7/4. And now let's raise each side to the 3/4 power. So c is equal to 7/4 raised to the 3/4 power. I think that's about 1.42. It's not, you can't, this is the exact, and this is how you would leave the answer. So, I think that's all we have to do. Oh, wait a minute, no, students, we're not done. I'm sorry. There's just a little bit more in here. The problems in the quiz will be like that. There's a little bit more here in these notes. And again, so there's a word problem here. I'll let you read that. Okay, so I'm not going to put word problems with the mean value thing. Eventually, pretty soon, we're going to get word problems with optimization problems, and there must be some of the harder problems in the class. So that'll be soon enough. Okay, so consequences of the mean value theorem. Okay, so this might be this is fun, and if you like math, this is fun. So, okay, so if you want to come back to this on a Saturday night, I go for it. Okay, so no. So if f is differentiable, and I like math. I like math a lot, actually. So anyway, so let's see here. So if f is differentiable and f prime of x equals 0, and on all points at some open interval I, then f is a constant on this open interval I. Okay, so so basically saying you have the derivative of a function is 0 for all values x, and then the function, it can be written in the form f of x is a constant, right? You graph the function, it's just this flat horizontal line. Okay, so here's our proof. Again, there's no proofs, and you're not, even if this is if we were having this in the classroom, I would never put a problem like this on the test. If there's a more advanced math course, yeah, then of course. Okay, so suppose f prime of x is 0 in this interval a comma b. Okay, so then okay, so you just choose any point a comma b. That's where this generalization comes in. By the mean value theorem, there's at least one point x in a comma b such that f prime of c is equal to the quotient f of b minus f of a over b minus a. But we're assuming that f prime of c is 0. That means that the numerator is 0, or f of b is equal to f of a, or f of b equals f of a. And the whole point here is that you choose f. You take, let a and b any points. Let's go back to here in the theorem. If f is differentiable and f prime of x equals 0 at all points on an open interval I, so let a and b be any points in that open interval I, and you can prove that f of a is equal to f of b. So you take any 2 points, okay? So that proves that f of x is some constant on this open interval I. Okay, so if the derivative is 0 on an open interval I, then the original function has to be a constant. And that kind of makes sense, right? Because you take the derivative of a flat line, you get just 0. Like when I say flat, you take the derivative of a horizontal line, you're going to get 0. Okay, so now here comes another theorem. And it seems pretty obvious, but if I say, okay, now prove it, maybe if you don't have these theorems, then it's going to be hard to prove, even if it is intuitively true. So functions with equal derivatives differ by a constant. Well, we know the derivative of a constant is 0. Okay, but now we're kind of we're going the other way around. Okay, so let's say the function is the equal derivative. We want to prove that like here. So let's say f prime of x is equal to g prime of x. What we are trying to prove is that f of x is equal to g of x plus some constancy. Okay, so well, first of all, so the function, if the function isn't equal, so let's take f of x minus g of x, and let's assume they have an equal derivative, then their derivative is going to be, right, so let's say f prime of x is equal to g prime of x, right? Then the derivative of f of x minus the derivative of this function is 0, which means that function, that means that f of x minus g of x is a constant, or f of x is equal to g of x plus c. Okay, and I think there's a few problems in MathXL, no, that MyLab that kind of use this fact right here. So look at these two functions here, f of x equals x squared plus 9, and g of x equals x squared plus minus 7, right? The functions